you've been watching my videos, then you'll know that I do a lot of repair work on vintage computer equipment like this. So quite often large boards with lots of TTL and boards like this, which is off a 4000 series PET. And one thing they share in common is they have large numbers of 74 series TTL devices on them. And one thing that I see quite frequently, and I think as Dave Jones would say, it's a trap for young players, is there are certain things relating to 74 series devices that is probably worth pointing out at this phase of this project. I have mentioned this in previous videos, and I said I'd do a separate video, and that's what this video is for. It's explaining some of the traps and pitfalls in using 74 series logic devices. Now, you're probably already aware that there are different series within the 74 group of TTL devices, and such as the LS series, the HCT, ACT, there's quite a wide range, and they do vary internally how their circuits are designed and configured, and they have different requirements for fan out, for example. They have different output voltage levels, different input voltage thresholds, so quite often you need to be careful when you're mixing them to make sure you don't encounter problems. That's not really what this video is about. I have mentioned those issues previously. What this video about is something a bit more subtle that can really cause some head scratching if you're not aware of it, and that is the different pinouts that devices with the same part number can have. So that's what we're going to look at in this video, and this is just an example of this sort of problem, but it's something that is fairly common, and I thought I'd show it on here because it's quite a clear example of the sorts of things you can encounter, and especially if you're working on something as complex as this board, if you're not aware of this problem, then you can end up just running in circles forever. And I thought I'd just share a bit of this and just go over some things I've learnt over the years that hopefully will save other people time. So the part of this system we're going to look at specifically is the baud rate generator. Very simple circuit. We've got a clock coming in, and then we have a series of binary dividers, and these are used to divide by 2 to give us the required baud rates. However, there are a couple of odd baud rates that we can't get just by dividing the fundamental clock frequency by factors of 2. Specifically, that's the 110 baud rate and the 1800, which is not a divide by 2 value. It's not in the divide by 2 series, so we can't obtain that directly just using a binary counter series. So the way this works is we tap off other clock values. In this case, we tap off clock 9, which comes from this pin, and we also tap off clock 5, and that comes from this pin. And the idea is what we then do is we use those tapped off values, so that these are, if you like, instances or states within the binary sequence, and by tapping them off we can get a different frequency. So what we're doing here is we're just using these 2 gates to couple the signal coming out of the particular pins on the divider chain through to the output, and the 7401 is, as you can see, it's a 2 input NAND gate, but it has open collector outputs, so they can be connected together, and we've got a pull resistor here to ensure that they can all be pulled up and we get the signal propagating through to the flip-flops as is intended. So what we're going to look at here is a very simple example of what can happen if you're not fully aware of different pinouts on the 74 series devices. So we'll look at this gate in particular. The board's powered up. We'll look at this device and we'll look at pins 4, 5 and 6 and see what we're getting out. So This is the device that we're talking about. It's the 74LS01, and we'll start by looking at pin 4. So we'll look at pin 4. As we can see, we're getting nothing out, and pin 4 is nothing more than the input from a pull-up resistor with a switch that can ground it through a buffer, and so all that we should see on pin 4 is either a high or low level depending on what we do with the switch. Pin 5 should be clock 9, so look at pin 5, and if we look on the scope you'll see that we do indeed have clock 9, which is 2.4 kilohertz, which is correct. And if we now look at pin 6, I'll turn all the switches off. So pin 6, we don't have any baud rate selected, so of course we're getting nothing other than the resistor pulling the line high. However, if I now turn on the DIL switch for baud rate 110, you can see that nothing happens. It's now on, we're getting nothing. If I turn on the baud rate for 75, you can see we're now getting a baud rate of 75, and that's at this pin here, so that's what we'd expect. However, we would expect to see the 110 signal when we turn the 110 switch on, and we're not seeing that. So if we now go back and the assumption here is, well, we've got something wrong with the track layout, so we'll go back, we'll have a look at pin 4 and see what that's doing. We know that the clock is on pin 6, so I'm now on pin 4. We'll turn on 110, and we're getting this very strange frequency appearing. It's not the frequency we were feeding in to the gate. So if I go back now and look at pin 5, you can see it's an inverted version of that, but if I turn the switch off, you can see the frequency changes. So something very odd going on. We're going from 2.5 kilohertz with the switch off. This is now all the switches are off, and this is the clock coming in. But if we now turn the switch on, you can see the frequency changes, which it shouldn't do. All that should happen here is we should gate the clock through to pin 6. We'll stay on pin 5, and I'll now turn on a different baud rate switch, and as you can see, nothing's happening. It's staying at the same rate. It's only when we turn this switch on that we start getting strange things going on around this gate. If we now go back and look at pin 4, so with the switch off we're getting a low signal here. It's inverted, of course, because we've got the inverter here, but the switch is open, so this input to the inverter's being pulled high, the output's low, and that's what we're seeing on the scope. If I now turn this switch on, so I'm going to turn on the 110 baud rate switch, you can see that we're now getting a clock signal appearing at pin 4, which is one of the inputs to the gate. So very strange. There are no other lines coming in here, and I have checked, there are no shorts. And of course at this point you start thinking, well, I've obviously got a fault on the board here, I've got a track that's wrong or something like that. I'll try turning this off. We'll come down here and we'll check the 1800 baud rate. So pin 8, just a high. I'll turn on the 1800 baud rate switch, nothing happens. We'll look at pin 9, I'll turn the switch back on, and the line's going high but still no signal. So we'll look at pin 10, and you can see we are getting the correct clock appearing there. So we'll go back to pin 9, and I'll turn on a different baud rate switch, and still nothing. So you can see that it's not working. This gate arrangement here is not doing what we'd expect it to do. It's kind of working in that it changes when we turn the switch on, but we're not getting the correct signal coming out of the gate. So as I said, you could be easily fooled here into thinking you have a fault with the board layout. what I'll do now is I'll swap this device for another 7401. I'll just turn the power off, and I'll now swap this for an alternate 7401. Okay, so we've got another 7401 in here. Looking back at the schematic, we'll go back to where we were looking before. So pin 6, I'll power the board back up. I'll now select the 110 baud rate, and we can see we are now getting the correct clock coming through. We'll go back and look at pin 4, and we can see that we're now not seeing the clock. If you recall, we were seeing a clock signal on this pin before. I'll turn this off, and you can see all what's happening now is it's going from high to low depending on the state of the switch, which is what it should do. Pin 5 of course has the clock, and pin 6 now shows the correct baud rate when we select the 110 baud rate switch, and of course we're still seeing the correct clock frequencies depending on which of the other switches we select. And the same with the 1800, that now works as well, so when I select that we're getting the correct clock frequency. Okay, so was it a faulty IC? Well, no it wasn't. This is what this video is really about. Whenever you're working on boards like this, and if you do a lot of work, then you tend to use a rule of thumb when you're fault finding. So if you're working on a PET, for example, if you come across a 7400, then in general the gates kind of point downwards in the package, so that's the inputs are the pins closer to the top of the package, closer to the pin 1 end that is, and then the outputs tend to be towards the bottom. And that's a fairly good rule of thumb, but it's not always correct, and that's kind of what we're looking at here. So what we have here is, this is a 74H01. The one I tried first was a 74LS01, but the issue is not whether it's an LS or an H. The issue is the letter after the part number. So this is a 74H01N, this is a 74LS01D, and I have another one here that also doesn't work. This is an AN. One of the odd things with the 74 series devices is that the N versions are in general a fairly standardized pinout. So they're the ones where the pins or the gates tend to point downwards in the package. Unfortunately, there are a couple of devices in the series that don't follow that same rule of thumb, and the gates point upwards rather than downwards. And then when you work out what the error here is, and you look at the schematic, it all becomes clear. If you imagine if you were to reverse these pins, then pins 5 and 6 would be inputs, and pin 4 would be an output, which is what we were seeing. It was just fighting with this inverter, and the same thing with this gate. And if we look at the package information on the datasheet for the 74LS01, it doesn't always help. So this is one that I downloaded, and we can see here that the gates are shown as pointing upwards. Doesn't help because it's not showing us the letter number, although it does give us different prefixes for the package type, but it's only identifying them as being ceramic or plastic or SOIC. So just looking at the specifications you can sometimes download doesn't always help, and you can see here that what we need on our particular schematic is for the outputs to be the higher pin numbers, or at least on the left hand side of the package. So in other words, this is wrong, this will not work on this board. Could of course relay the board to suit this, but in general if I'm doing a reproduction I'll stick to the original. So if you download a different datasheet for the 74LS01 and the 7401, so this is for both, it's 7401, 74LS01. Incidentally, 5401s or 5.4 series are exactly the same as the 7.4, except they're a much wider temperature range, but in general they will work just as well. But the same applies to them, and that you'll see that if you look at this particular data sheet, it's got both pinouts, but it doesn't really make it that clear as to which is which. It's saying this is the 5401W package, but this pinout is the 5401J, or the 74LS D or N, or the 7401N. That's not strictly speaking true, because the 5401 and the 7401 can share similar pinouts, so this doesn't really help as much either. You can then look at the much older spec sheet for just the 7401, and this can make things even more confusing because it's got multiple pinouts without really being particularly specific as to which one's which. But it does show that there's more than one pinout for the same device. And then of course you can download yet more data sheets, and this is a 74LS01, and again it's showing the incorrect pinout. It's got nothing to do with the fact it's the LS version, it's about the letter after the part number, and different packages can have the gates flipped around the other way, so they'll have different pinouts. I've mentioned this previously, but the only real safe solution is to get yourself something like this, a proper TTL data book. If I look up the 01 package, we'll see that immediately it becomes clear what the issue is, and also gives you the proper information. You can see that with the gates pointing upwards, this can be either a J, W, a J, an N, a J, or an N, depending on whether we're talking about a 5401, a 7401, a 54LS01, or a 74LS01. And you'll notice that the packages are different for different series. And this is what I meant about some not following the rule of thumb. In general, rule of thumb will tell you which particular one you're looking at just by looking at the letter designator, but some don't follow the same rule of thumb, so you need to look at the specific data sheet. And as you can see, we have 3 different variants here. There are some other 7.4 series ICs that have similar issues. The 02 is another one that has multiple pinouts. And there are a few others. For the most part, they do follow fairly standard numbering. In general, you'd be going for the N version, and that is the one that has the, if you like, the gates pointing down in the package, and that's the one that you will come across most often. But just bear in mind that something like the 01, that is the other way around. The N version has the gates pointing upwards, and you end up with a situation like this where you think you've got a problem with the board layout, and it's nothing more than an issue with the pinout of the particular device that you've got. And by the same token, you'll find that you'll put devices into a tester like this, and it will fail. It'll say you've got a fault, and it might just be that you've got the particular package that the tester's not configured to test, and it will come up with a fault because obviously it's not seeing the output signals it's expecting. So in short, if you encounter any problems like this and it looks like you've got a board layout or even a faulty device, make absolutely certain that you understand the pinout, and don't just assume that the first data sheet that you come across is the right one. So for example, if we were to look at this data sheet and assume that the pinout for the 7401 was the same as this, it won't match. The pinout of this device is not the same as this. And as I said, it's nothing to do with it being a 74H01. It's because it's a 74H01N. And what we need for this pinout is either a 74H01N or a 74LS01W, something like that, that will give us the correct pinout depending on the particular variant of the device. Okay, well I hope that made some sense. It's one of these things that you have to kind of come to grips with and get to terms with if you're doing a lot of this sort of work. For the most part, most devices you find will follow the rule of thumb, and it's fairly obvious when it's not the case. But just bear that in mind. If you're not seeing exactly what you expect, then don't straight away assume it's a faulty device or a short on the board or something like that. Just make sure you've got the right device for the data sheet that you're looking at.